Hi, everyone. Welcome to Lecture 6 of the Modern Machine Learning course. And in this lecture, we're going to build upon the results for the neural network Gaussian process and neural tangent kernel in lectures 4 and 5. And we're going to compute the neural tangent kernel for deep, fully connected networks. These are fully connected networks with more than one hidden layer. And we're also going to consider the neural tangent kernel for networks with other layer structures. In particular, the convolutional neural tangent kernel, which corresponds to the infinite width limit of convolutional neural networks. And we'll see that in practice, these kernels, solving kernel regression with these kernels actually gives quite good performance. And so what I want to do before I go into the derivations for the neural tangent kernel for a deep network, I just want to recall what we did last time. And this is just going to be a review of the derivation and origin of the neural tangent kernel. So remember that what we did is we thought of neural networks as maps on parameters instead of maps on data. This was our key insight. So neural networks as maps on parameters. And what we did is our first step was consider a linearization, which was we just took f sub x at w, and we approximated it by taking a first order Taylor series expansion of f around an initial set of parameters w naught. And this was exactly given by this formula. And we saw that this induced a kernel because we're thinking about training a linear model applied to transformed data. And so our feature map was exactly taking every x to this gradient vector. And so we saw that this introduced this neural tangent kernel, which we denoted k. And this is just the inner product of the gradients of f at x and the gradient of f at x tilde. Okay. So then what did we do? We computed some closed forms for this. So a closed form for the NTK of a one hidden layer network, which I'll just denote k superscript 1 of x and x tilde. And remember, we wrote this as the dual of x transpose x tilde plus x transpose x tilde and the derivative of the dual at x transpose x tilde. And this was if your data lied on the sphere. We had this simple formula. And so remember what phi check mark is. This is the dual of an activation phi. Okay, so what we're going to do, well, lastly, what we did, we're not going to extend upon this in this lecture, but we showed that we connected solving kernel regression with the NTK to training all layers. This is all layers of an infinitely wide neural net using GD, gradient descent. So this is what we did in the previous lecture. What I want to emphasize now is we're going to take this formula for the NTK for a one hidden layer network, and we're going to recursively compute the NTK for a network with L hidden layers. And what does this actually look like? So what is a network with L hidden layers? Remember that before I pictorially drew what a neural network looks like, a fully connected neural network. For one hidden layer, looked something like this. Remember we had our matrix, before we called it B and A. In this lecture, I want to call it W1 and W2. So we had a matrix W1 and W2, and this was a one hidden layer network. Now what we're going to do is consider a setting where we have L hidden layers. So we have an X coming in. You'll have a weight matrix W1, a weight matrix W2, and all the way down, you'll have a weight matrix on the last layer, which is just WL plus 1. And this will give us our output Y. And this is going to be a L hidden layer network. And we're going to compute the neural tangent kernel in a recursive fashion as all of the widths of these networks, as the number of hidden units for each layer goes to infinity in a particular order. And so let's get into a description of how to do this. By the way, why would we want to do this? Why would we want to compute the NTK for a deep network? Shouldn't the one hidden layer already be good? It can fit pretty much any data set. It's a kernel. Well, it turns out that in certain cases, maybe you see that a deep neural network is actually beneficial for your task. Having more than one hidden layer is actually good. In fact, this will be the case for convolutional neural networks, but this is still an active area of research to understand how much depth is useful for predictive tasks. But what we'll see is we just want to show that we can get the flexibility that we had with neural networks with kernel methods, and consider a variety of kernel methods. So if a deep neural network is working well, we should be able to compute the CNTK for the corresponding network and have a richer class of kernels to work with. Okay. So let's first write our description let's write down a closed form for what a neural network with L hidden layers actually looks like. So before I had written this as A5BX, now we're going to write it in terms of these general layers. So I'm going to have these L plus 1 weight matrices, and I'm already going to introduce this NTK style normalization. So before, remember, we were multiplying in A5BX, we multiplied by this additional scale factor 1 over root K, which was 1 over the root width, or number of hidden units. Here we're going to have multiple scale factors. And I'll exactly define the shape of these matrices in a minute, but we're going to have these additional scale factors, which are our 1 over root KL, 1 over root KL minus 1, and so on, all the way down to 1 over root K1, phi of W1x. Okay. And here, our matrices Wi live in real values from Ki by Ki minus 1. These are matrices, so size Ki by Ki minus 1. And because our data is in RD, we better have that K0 is the dimension of the data, D. And as our function, our neural network is predicting a scalar output. It better be the case that KL plus 1 is exactly 1. And of course, we have the standard phi is an element-wise activation. Okay. So now I just want to note briefly, because it'll be useful for our proofs later, there's a nice recursive form. So this is the full expanded out form for a neural network. And again, I'll highlight the scale factors in red here. But now I want to write a nice recursive form, because it'll be useful for me later on when I compute the neural tangent kernel. And in particular, the form that I want to consider is I want to write, I have these hj's of x, which are just given by 1 over root kj, phi of wj, h of j minus 1x. And I'm going to set my initial condition, h of 0 is just x. And then I'm going to write fl at x and w is just exactly w at l plus 1 times hl of x. And here I'm going to let my indices j run from 0 to l. And here I'm just going to consider, we already have the initial condition 0, so I'll just consider j 1 to l. Okay. So now what I want to do is compute the neural tangent kernel for this network. And remember, there's only one trick to doing this. If we denote our neural tangent kernel as k x x tilde, well, we don't know much about some clever formula for this without working through the original definition. And so what is the definition? Remember on the last slide, we just recalled it. It's just the inner product of gradients of FL at W at some data point X with the inner product of gradients at F at X tilde at W. And here I'm just going to say this W is our initial value, W naught. This is going to save me some notation. Okay, so now we've reduced the problem of computing the neural tangent kernel to just computing an inner product of all of these partial derivatives with respect to every parameter here. And so how are we going to do this? Well, let's just write out that, let's write out the theorem first for what the neural tangent kernel will be, and then we'll get an intuition as to how to prove this. So let FL of X at W be a L hidden layer neural network as above. And now consider the case where all my parameters, so all the parameters in W here are sampled IID from a standard normal. Then as, and also consider the case where we're on this sphere. So all our data is operating on the unit sphere in d dimensions. And let's also assume that our activation function is normalized such that phi, the dual at 1 is 1. Then, as these layer-wise widths, k1, k2, kl go to infinity in this order, in particular, k1 goes to infinity first, k2 goes to infinity second, and so on, the neural network Gaussian process, which we denoted sigma of L, and the NTK, which we denoted as K of L, are given by sigma of L, has to operate on 2 points, x and x tilde. This is just the dual of sigma L minus 1 at x and x tilde. And sigma of 0 is just x transpose x tilde. And similarly, we have KL of xx tilde. This is going to be surprisingly exactly the neural network Gaussian process plus some correction term. And this correction term is exactly the following. It's the derivative of the dual at sigma L minus 1 at xx tilde times the kernel. So we have this recursive formula. And our initial condition here is just that the kernel at 0 is again x transpose x tilde. Okay. So I just want to note a couple of things here. Maybe I'll just draw a line here. So this is the theorem, and this is what we're going to prove. But we've already established this result for certain cases. And in particular, we did this for the case where L equals 1. So remember that for L equals 1, sigma 1 of xx tilde, this is what we did in lecture 4. This is exactly the dual of x transpose x tilde. And that is exactly what we have from this initial condition here. And similarly, so this now equals sigma of 0 of xx tilde. So this is a check. Now remember, K1 we did in lecture 5. This is exactly, well, remember it was this dual, I just wrote it on the previous page, but it was exactly the neural network Gaussian process plus the derivative of the dual at x transpose x tilde times x transpose x tilde. Well, we can see that this x transpose x tilde is exactly k0 of x tilde. And then this derivative of the dual here, we would just substitute in sigma 0. And so we get exactly this formula here. And this is, again, another check. So the formula holds for the case when L equals 1. And so this should give you some intuition as to how we're going to prove this. The idea is if you see it holds for this one step, we're going to use this as the base case for inductive proof of this theorem. And so let's actually go to that inductive proof. What I'm going to want to do is actually copy our nice recursive form and this form for the neural network, since these terms will come in handy. Okay. Okay, so let's now, given this, let's start proving the theorem. And this is going to be by induction. And on the previous slide, we actually just checked the base case for when L equals 1. So now let's just assume this, assume that the statement is true for a neural network of depth. So assume true for a network of depth L minus 1. And so now the question is, how do we prove the two statements for a network of depth L? Well, we're just going to exactly turn to the definitions. So let's start with the neural network Gaussian process. And we'll see that the neural network Gaussian process is not so bad to do. The NTK is going to be a little bit more involved. It's going to involve keeping track of some extra bookkeeping with some indices and variables. But really, all of the computation is the same as from this neural network Gaussian process. And so what is sigma L of x tilde? Well, remember, all it is, the neural network Gaussian process arises as a result of fixing this whole representation and just training the last layer of our neural network. And so what is this whole representation? Well, this whole representation that we had written out here, including this extra square root 1 over square root KL term, that is exactly h of L. That's how we've defined it. So it's just exactly going to be this inner product of h of L at x and h of L at x tilde. Okay. So now we can just start expanding this. Well, this is going to be, I can pull out, we're going to have two 1 over root KL terms that come in here. And so we can just pull those out of the inner product. And now it's going to be an inner product that looks very similar to what we had seen in the past. And I'm just going to write it as HL minus 1 of x. Oops, and I forgot that, of course, here we're considering the limit where KL goes to infinity. We want this infinite width neural tangent kernel. And then, substituting in for HL of x tilde, we just get the following. Okay. But now we know how to deal with such things. Remember that this is very similar to the neural network Gaussian processes that we had considered before. Remember, this is just a sum over KL terms. These are vectors in RKL. And this is exactly W at L I colon H of L minus 1x phi of WL I colon H of L minus 1 x tilde. Okay, and so we can write this as an expectation over some isotropic vector W, and this is exactly W transpose H L minus 1 of x phi of W transpose H of L minus 1 x tilde. Oops, not an inner product here, it's just an expectation. And now, remember we did our trick. This is just, I can rewrite it as a bivariate expectation over some covariance matrix, which I'll call lambda L minus 1. So this is an L minus 1 here, of phi of U, phi of V. This is exactly how we computed the neural network Gaussian process. But now, what is this lambda L minus 1? My claim is that by the inductive hypothesis, this lambda L minus 1 is exactly sigma of L minus 1 x, sigma of L minus 1 x tilde, sigma of L minus 1 x tilde x, which by symmetry is the same as x tilde, and then sigma L minus 1 of x tilde. And this is just a 2 by 2 matrix. So now why is this the case? Well, remember, what is the entry in any of these coordinates? Let's look at this entry. This is just exactly the inner product between HL minus 1 at x and HL minus 1 at x tilde. But remember, we had considered in our inductive hypothesis that all of those widths, K1 to KL, were going to infinity in this specific order. So KL minus 1 has already gone to infinity here. And so in this case, this inner product is exactly sigma of L minus 1 x tilde. That's just by our inductive hypothesis. That's what we had started out with here and what we were trying to prove for L, but we assumed it was true for L minus 1. And so we are good to go. Because now we have a nice clean form for the N and GP of a depth N network. But now here's the big catch. So let me just move this computation a bit, make some room. Oops. Actually, let me just cut this here. Okay. So now we have this form for the N and GP, but it actually doesn't tell us. We need to somehow connect it with the dual, and this is where our assumption comes in. So remember, we had assumed that phi check mark at 1 equals 1. And what I'm going to ask you to prove in the homework, it's really not so bad, you can also do it by induction, is just that this implies, if your dual is normalized in this way, then all the way through all the way for any x in the unit sphere, all the way through layers L minus 1, the sigma L minus 1 at x is just going to be 1. And so what does this mean? Well, this means that I can cancel here these two terms and replace them by 1s. And so if you recall, the definition of the neural network, the definition of the dual, remember we just put a row in these two coordinates. And then we had exactly that this was the dual of rho. But of course here rho is exactly sigma of L minus 1 x tilde. And so this is the proof for the recursive formula for the neural network Gaussian process of depth L. We see that it exactly follows the recursion that we wanted. Okay, so this was the NNGP. The neural tangent kernel is just slightly more involved, but it's just, again, computation. And I've written it out cleanly in the notes, but we'll go over it briefly now. I'm again going to want to copy this formulation since it'll be useful for our derivation. Okay. And so remember, at the end of the day, all we're doing is just finding a clever way to compute an inner product of all these partial derivatives. And so really it is sort of a calculus 2 type problem, but we just have to have a clever way of handling this. And that's the trick. It's really just all about bookkeeping these indices. And not to say that that's easy in any way. I've stumbled on this computation many, many times. So I think it's worth going through a bit slowly here. Okay, so what is the definition of the neural tangent kernel? Remember, this is just the limit as this KL goes to infinity. At least this is the setting we're considering, this infinitely wide neural network. We want to consider the inner product of f at w, f sub x at w, with f sub x tilde at w. Okay. So now let's just exactly write out what this is. Well, we're going to shorthand this a bit. So first of all, we're going to want to write it in terms of two inner products. And what we're going to want to do is, first of all, we're going to consider all the partial derivatives with respect to the entries of WL plus 1. And the reason we want to do this is that we're trying to find a recursive formula for the gradient of a depth L network. So we want to first write it as a recursive formula in terms of, we want to somehow have enter into this formula the gradient of a depth L minus 1 network. And to do that, we're just going to subtract out these components that correspond to the new parameters. And that's exactly what we're doing here. So I'm going to write this in red here. So first, I'm going to group all of the parameters. This is just going to be I equals 1 to KL. I'm just going to group all of these inner products with respect to the W1I L plus 1. So this is the new parameters that I introduced when I have a network with depth L. Okay. Now what I'm going to do in blue is just consider this inner product of gradients with respect to W tilde, which is going to be all of my other parameters. So WL, W2, all the way down to W1. And so this is the big trick. We're going to evaluate the red part separately and then the blue part. And we'll see that the blue part actually is a little bit tricky, involves some computation in terms of the NTK for a network with multiple outputs. This is a little bit tricky, but I'll write it down here. And now we evaluate this red part. So let's just copy this part here. How do we evaluate this? Well, it's actually not so bad to compute these derivatives. So let's just do it here. So we're again taking this limit as KL goes to infinity. So what are the derivatives with respect to all of the other parameters? Oh, sorry, with respect to these outer parameters, W at L plus 1. Well, this is exactly, if we're looking at this definition of F here, you see that it's just exactly the ith value of HL of X times the ith value of HL at X tilde. Okay, so this looks like an inner product of HL of X and HL of X tilde. So this had actually better look familiar now. We just did this computation. You see that term exactly appears there. And what is it? It's the neural network Gaussian process for a depth L network. So that was easy. We have already done this computation. So this is exactly sigma L of X and X tilde. So now all that's left is to compute this blue term. And actually, if we go back to our formula, what should the blue term be? Well, you see the blue term should exactly be all of this. So we need, let me just rewrite this here properly. So we need to show that our term in blue is somehow the derivative of the dual and of the Gaussian process of a L-1 layer network times the kernel of an L-1 layer network. Oops. Okay, so this is actually going to be a little bit tricky, so we'll go a little slow here. And we'll again copy our favorite set of formulas onto the next page. Oops. Okay, and I also want to copy this term here. Okay. Okay, so we're evaluating this thing, and we're evaluating this as limit as KL goes to infinity. Great, so now when we do this computation, what we want to find is a term that looks like the inner product of gradients of an L-1 network, of the function output of an L-1 layer network. And the reason is that we wanted to get out in this term the kernel of the neural tangent kernel of a depth L-1 network. And so this is exactly what we're going to do. But first, before we do this, before we consider this, let's actually consider what one of these partial derivatives looks like. So we just want to analyze the partial derivative. So this partial derivative of here with respect to one of the parameters, and I'm just going to call it WAB to the L, little l. And here, this is just going to be one of my parameters in WL, WL-1, all the way down to W1. Because these are down, we've already handled the case of these parameters here. Okay, so what exactly is this partial derivative? Well, you see again that it's now going to be, we have to do some jugglery here, but we're going to look at this style of equation. And so first of all, what is that? That is going to be a sum from I equals 1 to KL of W I of L plus 1 times 1 over square root of KL. Here I'm now substituting in my representation for H of, and you see my parameters now enter into this recursive formula. So I'm going to have a phi prime of Fx at L-1 of Wi. And here I actually want to write it in terms of these W tildes, because of course in my L-1 layer network, there's no parameters that are capital W of L plus 1. So just denote that W tilde of I times my partial derivative with respect to this subnetwork. So all we've done is just use the chain rule and move this partial derivative computation into this L-1 hidden layer network. And here what I've used is the fact that H of L of X, which is just exactly 1 over square root KL, by WL H of L-1X. Remember that this, by definition, is just Fx L-1 at W tilde, which is just W tilde is my notation for this new set of parameters that's contained in the subnetwork given by Fx of L-1. Okay, Okay, so now that we're given these two, let me actually move this over here. So now that we're given this formula for these partial derivatives, we know what this limit actually is. So this limit is just exactly, limit as KL goes to infinity. It's just going to be a sum over this product of all my partial derivatives. So I'm just summing over all my variables, WABL, of these partial derivatives. Oops, WABL times partial fx tilde at L divided by partial WAB at L. And so all we need to do now is just substitute in this expression. And one thing to keep in mind, which is a very subtle detail that I often get tricked up by, is that the L-1 layer subnetwork given by this fx, L-1 and W tilde, this is a network with multiple outputs. In fact, it has KL outputs, but notice that we're taking the gradients with respect to one of these outputs, and this is in particular the ith output. And so what we've done is actually somehow reduce the gradient computation to the case exactly to what we wanted, which is just a neural network with this one output, which is just the ith output. And before I continue, there's one subtle property here, which is that if I accumulate all of the gradients with respect to this ith output, and if I do the same with respect to another output, this I prime output, this is actually going to be a neural tangent kernel of depth L-1. It's going to be there's an X tilde here. This is exactly what I want if and only if I equals I prime, and it's going to be 0 otherwise. And why is this? It turns out, because of the fully connected layer structure, the last layer, you have all of these independent Gaussian random variables that are independent across the different rows. And this gives this independent structure, lets you do this type of computation. And for those of you who want to make this very rigorous, I encourage you to try to work this out. You'll see that you just have a bunch of different independent variables, these with respect to the last layer come in here. And when you take expectations, you'll see a bunch of zeros that appear. Okay. So now how are we going to do this? Well, let's just now return to our computation. We just want to substitute this expression in star up here, all the way down here. So I want to take this limit as KL goes to infinity of summation WABL. And now I have a giant mess of terms. I'm actually going to have a summation I equals 1 to KL, WI L plus 1 over root KL. Let me do this. Let me draw a line. Let me draw a little box so that these don't get confused. Phi prime of fx at L-1 at W tilde I times the, actually, because we're running out of space on this one, I'm just going to copy these over to the next page. I want to copy all of this over. Okay. Now here, what we had from before is just the partial derivative of f L-1 at W tilde I by partial WAB, the L. Okay. Now we have this times the whole other side. So we need to substitute in for this term here. So we have another product. So this is the whole thing times summation I equals 1 to KL, WI at L plus 1 over root KL, phi prime fx at L-1, W tilde I times partial f x tilde L-1 So again, as I mentioned, it's just a lot of variables to keep track of. But that's about it. It's just a clever way of keeping track of variables. We'll just give you this recursive formula. So I know it might be daunting at first, but I encourage you to look through the lecture notes and try to work this out carefully if you're interested in this style of computation. Of course, what I'm going to do now is I have a product of two sums. I'm going to write it as a double sum here. WABL. I'm writing it as a sum over I and I prime, both of these varying from 1 to KL. Now I'll have a WI at L plus 1, WI prime at L plus 1. I have a 1 over root KL and a 1 over root KL here. These are going to come out of my computation, and they'll just come out and form a 1 over KL outside. Then I'll have a phi prime x of L minus 1 at W tilde I, phi prime f of x tilde at L minus 1, W tilde I prime. And then I have my two partial derivatives, which instead of writing to save time, I'll just copy them. Great. And then maybe I'm running out of room, but we'll just write it off to the side here. Okay. Okay. Now we're going to do everyone's favorite trick, which is just swap the sum, the order of the sums. I can do this right now. I don't have any infinite sums going on here. So I'll take my limit KL to infinity. I have a 1 over KL summation I prime equals 1 to KL. I have this massive set of terms. Okay, and just to clean this up a bit, maybe I'll draw a line here. A line in black to separate this. Okay. And now, don't forget that my sum, actually just erase some of this stuff here. Let's move it here. Oops, I have to copy this one. Okay. So now my sum is exactly over the WABLs here. I have this whole thing times this. Okay. So now we can actually recognize in black here, this sum is actually just what we wanted. It's this inner product of gradients of an L minus 1 layer network. But remember, remember that this sum from the previous page is only non-zero. So it's KL minus 1 of x tilde if I equals I prime, and it's 0 otherwise. And so that means that when we sum over all of these indices, I and I prime equals 1, we actually only want to consider the case where I equals I prime. Because otherwise we get a 0 here, the whole sum is neutralized here. So this will actually end up being the sum, the limit as KL goes to infinity, sum 1 over KL, I equals 1 to KL. Now here, when I equals I prime, I just get a WI at L plus 1 squared, phi prime, f sub x at L minus 1, W tilde I, phi prime at f sub x tilde, L minus 1, W tilde I, times k of L minus 1 at x tilde. And now we're really in business because we already have this recursive part here. And we already know what this sum is going to be. The reason we already know this, remember that this is going to be a giant expectation over these WI at L plus 1s, which are independent of all of the entries in W tilde. So we know that this expectation of WL plus 1 squared, WI L plus 1 squared, this is just going to be 1. And we're going to get an expectation. So this whole thing is going to be in an expectation. If we remember what our fx of L minus 1 at Wi is, well, it's exactly phi of W transpose H of L minus 1 at X at I here, and then times phi of, well, let me make sure I copy this over correctly. Nope. That's right. It's going to be exactly this expectation here, where there's 5 primes. Okay. And you saw the reason I went back to that previous page is because this expectation had better be the neural network Gaussian, the derivative of the dual of the neural network Gaussian process between x and x tilde. Perfect. So at the end of the day, what have we actually done? Let's go back a few pages because I had this written out here nice in red and blue. We showed that this term in red is exactly this neural network Gaussian process of a depth L network with respect to x and x tilde. And then we showed that this whole thing here is exactly KL minus 1 x tilde times the neural network Gaussian process of x tilde of a depth L minus 1 layer network, evaluated as the input to the dual activations derivative. And this actually proves the theorem. And I'll just state the theorem again because I know this is a lot of derivations and a lot of computation. I've written it out again in the notes for anyone who wants to go through the detail. But at the end of the day, the result that we have is that the depth L NTK is exactly the depth L NNGP plus the derivative of the dual of an NNGP of a depth L minus 1 network times the NTK of a depth L minus 1 network. And now, recall that we had also proved that the depth L and NNGP is actually the dual of the depth L minus 1 NNGP. This one has a very simple and easy to remember form. But what are our initial conditions? It's just that the kernels at depth 0, remember these are just linear networks, so their kernels better be the linear kernel. And so that's it. So we have now a closed form for the NTK for a depth L network. I do just want to mention, as this is a very trivial corollary, that if we just think about, if we denote by phi n of psi, the composition of psi with its of phi check mark with itself n times. So what I mean by that is I just do this function iteration n times. Then the NNGP and NTK can actually be written very conveniently as the iteration L times of x transpose x tilde, and the NTK is exactly the NNGP plus the derivative of the dual of the function phi checkmark iterated L minus 1 times the kernel at L minus 1 of x tilde. Great. So wherever we saw the NNGP, we just replaced it with its function iteration form. Okay. So usually this is one of the most concise ways to remember the NNGP and NTK. And of course, this is all under the condition that you have your data on the sphere. Let's not forget that. And also that the dual was normalized so that phi checkmark at 1 is 1. Of course, there are neural tangent kernel formulas when your data is not normalized. And in fact, in the homework, there's a simple trick for taking the ReLU of taking the normalized ReLU and transforming it so that when your data is no longer on the sphere, you can write out this formula. It's just a little bit more involved, and I think it's a little bit harder to parse what's going on in this theorem when you have the general formula. Okay. Of course, one other thing to keep in mind is that we just went through this derivation once. Why did I go through it, even though it was tricky? The reason is that in practice, when you actually want to, let's say you have a new neural network architecture and you want to consider the infinite width limit, it's usually a good idea to have understood how to compute the NTK from scratch, as opposed to just using a library like the neural tangents library. And the reason is that for research purposes, usually we have to come up with the neural tangent kernel ourselves. These are not already usually implemented when there's novel architectures that we want to work with. And a prime example I'll cover in the next lecture on matrix completion with the NTK. On the other hand, if you don't care about this research aspect of coming up with new neural tangent kernels, what you have, you never have to actually go through this computation. The neural tangents library, which I'll again write down here, and you will go over in the homework. This lets you very easily compute the NTK just from a template. So I would give you a neural network architecture, or you would give it a neural network architecture, and it would output for you the corresponding neural tangent kernel and the neural network Gaussian process at the same time. And the reason is that the neural tangent kernel already computes the neural network Gaussian process along the way. That's how a lot of these libraries work. And so it's a really convenient tool. And we're actually going to make use of this tool for the next part, which is going to be the neural tangent kernel for convolutional networks. And here, I'm not going to do any more calculations because these calculations are quite involved. What I'm going to do instead is just give a high-level intuition about why the convolutional neural tangent kernel, the CNTK, is different than the fully connected neural tangent kernel. In particular, what we'll show is that if you have some images, instead of being a kernel on pairs of images, the convolutional neural tangent kernel is actually, for at least fully connected networks, is actually a kernel on all coordinate pairs across all pairs of images. So it's a very large kernel, and it's actually very expensive to compute unless you're using some tricks. And I will go over some of those tricks in this lecture. Okay. Before we do that, though, I know some of you might not have heard of convolutional networks. And so I just wanted to give a brief refresher on what this actually is. So let's say we're given some image. In this case, my image is just going to be a 3x3 matrix. And let's say I'm going to call this image X, capital X. And let's just say for now it has the values 1, 2, 3, 4, 5, 6, 7, 8, 9. And typically, pixel values you'll see from the range 0 to 255. So this would be a very dark image. And people typically normalize these so that you just divide all the pixel values by 255, and it'll be in the range 0 to 1. But just like we did a one hidden layer fully connected network, we're going to define a fully convolutional network. And this is just going to be a network where I do f of x. Here x is now is a matrix. It's going to be something that I call A star 1 over root k phi of B star x. And for those of you who are familiar with convolution in signal processing or Fourier analysis. This is not that convolution. This is a weird version of 2D convolution. And the way this works is that this B, I usually write it in this weird form. It's going to be a 4-dimensional object in some way. And I'm going to call it K by 1 by R by R. And then A, we're going to write it as a 1 by K by R by R. And the way to think about these is I think about so ignore the K and 1 right now. Let's just look at an R by R matrix. I'm going to typically take R equals 3 because that's what people use in practice. So B, I'm going to think about as K 3 by 3 filters. So these would be 3 by 3. And I'm going to think about A, this is all B. A is going to be one giant filter, which has a volume. So it's going to be a stack here of depth K. And you have these 3 by 3 filters running down this long horizontal stack. Okay, and how do these filters actually work? What is the star operation? Well, I'll write it down mathematically first, what the star operation is, at least operating on this input here. So I'm going to index these K different filters by B1 through BL. And the way it works is if I'm just looking here at phi of B star X times this 1 over root K, I'll keep that in there. And if I call this Z, Z, L at IJ is just going to be 1 over root K sum, because I have these 3 by 3 filters, it's going to be over indices A and B and -1, 0, 1 of BL at AB times X at I plus A, J plus B. Let me copy this over to the next page. And I think the formula is there. The formula will be useful for computing gradients and partial derivatives when we want to compute the CNTK. But really, visually, it's much easier to understand what's going on. So what does this actually look like? So let's say X is again our image, which has 1, 2, 3, 4, 5, 6, 7, 8, 9 as its entries. What I'm actually going to do is expand X by 1 extra coordinate in each dimension here, and I'm just going to pad it with these zeros. So X has now become a 5 by 5 image. Now what I'm going to do, by the way, this is called zero padding. There's other types of padding you can do. But what I'm going to do with each of those filters, BL, remember, this is a 3 by 3 matrix. And let's just make it a matrix of all ones. This will serve our purpose. So if I want to compute Z at L, what I'm going to get back is it's going to be a 3 by 3 image. Now this first coordinate here, what I do is I will literally take this filter here and slide it over this position, this 3 by 3 position, and just do this element-wise dot product. So what I'll get is I'll get 1 times 0. So it's in the upper left corner. I'll in fact highlight the region here in blue. I'll get 1 times 0 plus 1 times 0 plus 1 times 0. That's the top row of dot products. I'll get a 1 times 0, a 1 times 1, a 1 times 2. That's the middle row. Then the last row is just a 1 times 0, 1 times 4, plus 1 times 5. So all in all, this is just going to be 1 plus 2 plus 4 plus 5 is 12. So I'll put a 12 in this upper left corner. And now, if I want to compute the next set of entries, I just slide my filter over by 1. And again, it'll be this computation. You'll see that you get 1 times 1. So this is this first entry. You'll get a 1 times 1 plus 1 times 2 plus 1 times 3 plus 1 times 4 plus 1 times 5 plus 1 times 6. This is just going to be 10 plus 11 is 21. And please forgive any arithmetic mistakes here. Okay. And so on. And this is how you fill out this intermediate representation C, or ZL. And so what is my final output of the neural network? Well, this final output for any coordinate ij is just, again, remember we had this now big volume that we were doing this dot product over, this A, which is one giant filter of size k. It's just a sum from L equals 1 to k of A sub AB at L times Z of I plus A, J plus B at L. So again, it's this convolution operation. We're sliding that giant volumetric filter across here. Okay. And honestly, this is a lot. I honestly recommend, if you haven't seen convolution before, there's a lot of nice animations online for doing this. I actually preferred Andrei Karpathy's original lectures on convolutional neural networks. I forget the name of the course now, but it was a Stanford course. And he had some very, very nice, and I think the YouTube videos are available, and he had some very nice lectures on this. So I encourage everyone to go and check those out, and I'll make those available in the lecture notes as well as a reference. Okay. So now, given this convolution operation, nothing changes. If we want to compute the CNTK, all we do is take now this neural network architecture. We take this limit as k goes to infinity and take this gradient of inner products. So we just look at the gradient of f with respect to all of these weights. Now we have these filters, we have these shared weights, but it doesn't matter. We're still taking these gradients with respect to the weights. And so this is it. This is going to be our CNTK between x and x tilde. Okay. But now there's something a little bit weird here. And the reason is that, remember, in the NTK case, we could do this because all of our outputs were one-dimensional. And when you had multivariate outputs, the rows were somehow independent of each other. And so you could just compute the NTK for one output neural network, and you were fine. So this is exactly what we did for fully connected networks. So now we have to be a little bit careful. We want to try and apply this formula pretty much the same way for convolutional nets, but there's something a little subtle, which is now that every pair, every entry, these are no longer independent outputs. So remember, my output is actually an image, and if I was to draw the convolutional net, I have my matrix X, let's say capital X going in. This is my image. I hit it with B, and I get a set of K 3x3 matrices here. So there'll be K of these. That's exactly what B produces. This is my ZL. This is my Z, but it has L from L equals L and K. And then I use my A matrix to compress this all back down into one image. And this is my output, f of x. Now the entries of these outputs, they're no longer independent in the same way. I'm sharing parameters, so I cannot do this trick anymore. And so what I do is when I have a loss, remember what my loss function is. Let's just say I have one pair of images and targets y. My loss on my parameters a and b here is exactly going to be 1/2 sum. If I have a general p by q image, I'm going to sum over all the coordinates I equals 1 to p, j equals 1 to q, y ij minus f of x ij, f of x ij norm squared. And this is my standard mean squared error. Let me actually just move this over, give myself some room. Oops. Okay. So now, because these indicators or these entries are no longer independent of each other, I can't just use my standard, neural network, neural tangent kernel trick where I consider one of them and compute the gradients with respect to that. I have to do a trick to handle this. And the big trick is to actually realize that the convolutional neural tangent kernel is not just acting on pairs of images, x and x tilde, it's actually acting on pairs of all pixel coordinates across all image pairs, x and x tilde. And what I mean by this is the following. We can actually take this loss and rewrite it as follows. Oops. I equals 1 to p, j equals 1 to q, norm yij minus, I'm going to introduce an extra matrix here called mij, and then compute this inner. This is, again, a form of inner product called a trace inner product. And this is just the inner product between these two matrices. And what is mij? Mij is just a big matrix with zeros everywhere, except it has a 1 in the ij entry. And this is called an indicator matrix. Or we will call it an indicator matrix. Okay. So now, what are we actually doing? Well, here, you see, we're going to rewrite this as a function of mij and f of x. Well, in particular, it's just a function of mij and x. And exactly, this function is just what we wrote before. And now what we can do is g of mijx, this is a real valued function. Its output is a real value. So we can actually compute the gradient with respect to the output of g of mijx. And that is exactly what the neural tangent kernel will be, this convolutional neural tangent kernel. I'll denote it as k sub c. It's no longer a kernel on just x and x tilde. It's actually going to be a kernel on mijx and pair mi prime j prime x tilde. This is going to be our neural tangent kernel. And what space does this live in? Well, if I have p by q images, well, this is first of all a real value, but if I look at, if I have n images, so if in my training set, so if my train set has n images of size p by q, and I'm doing a fully convolutional network, this is always the case with a fully convolutional network, my CNTK for the training set, when I compute my training kernel matrix, this is actually going to be, I have to go over all pairs of coordinates of which there's PQ, and I have to go through all of these image pairs. So it's going to be a PQN by PQN matrix. So this thing can be very large. But as we'll see, in the next lecture for image and painting, we're going to use exactly this trick when n equals 1 and get some really cool results that match the performance of convolutional networks for this problem. But the thing is, when we have this general kernel matrix, the CNTK of size PQN by PQN, even though it's difficult to compute, if instead of using a fully convolutional network, you consider network architectures where you have a fully connected layer at the end, there's a nice way to reduce this down to a n by n matrix. And that is exactly what the original CNTK paper by Sanjeev Arora's group did. And so we'll just review what some of those architectures look like. Again, we're not going through any of these derivations. For those of you who are interested in these derivations, I encourage you to just look at those papers. But for a fully connected, what I'll call a fully connected convolutional network, what we have is we have visually an image X coming in. We'll apply our convolutional layer and get these K representations. Remember, we'll have K representations here. And I'll call this again my Z, indexed by these indices L. And now what we do is we take this output and we flatten it into a giant vector. And then apply our usual fully connected matrix, and we can get our outputs again. So this is one option for converting a convolutional network into a into a classifier where you just want maybe one output. Another option is to do something called global average pooling, and this was actually introduced in this paper that computed the CNTK for the first time. And it's an interesting idea. And even though it doesn't look too different, all of these steps for the first part are the same, which is why I'm just copying them over. What happens is that when you do this, it will fundamentally change how you use the CNTK. So what we'll do is just take a mean over each of these representations. And I'll call them mean 1, mean 2, up to mean K. And so this will be, you have some K dimensional vector now. And then I just convert it into, I use a fully connected layer, and I convert it out here. Sorry, not a fully connected layer. I just average over all of those means. So again, I take another mean here. Okay. And this is how I'll get my output Y. Great. So now if you do this operation, where we just took the mean over all of these, what happens is that we reduce the CNTK down in a drastic way. So remember, the KC for a convolutional network before, it was this kernel that operated on all pairs of all coordinates across two images. And in particular, let's say we just had n equals 1. We had one training sample. This training kernel matrix is a PQ by PQ matrix. And so if you use this fully convolutional network, the way you reduce this down to one value, so for n equals 1, we should have a training kernel matrix of size 1. It should just be a scalar. And the way you reduce it is you actually just take the trace of this matrix. That's what the corresponding convolutional neural tangent kernel looks like for this fully connected convolutional network. If you do the same thing for the global average pooling network, what it actually does is it just takes a mean over this. So it's just going to sum I equals 1 to P, sum J equals 1 to Q, 1 over PQ, oops, 1 over PQ, K hat, IJ. Great. And actually, I do want to clarify, I made a typo here. This is actually a weight matrix. You'll have some weight matrix in A. Okay. But the key thing is that you first take this mean before you apply this weight matrix. Okay, so you can see that the two different layer choices here have two very drastically different effects on the kernel. And now, the key thing, or one interesting finding, is that this one is very expensive to compute. You actually have to end up computing the giant PQN by PQN matrix and then averaging over all of these things. It's a bit of a pain to compute. On the other hand, this trace requires only knowing the diagonal entries of this K hat. And so this is actually quite fast to compute. And there's tricks. You don't have to compute all the entries of this PQN by PQN matrix. And so this is the nice trick with this convolutional neural tangent kernel. But sadly, one thing is that, one interesting finding is that global average pooling networks with this have a drastic boost in performance over networks where they have a fully connected layer at the end. And so all of the exciting close to state-of-the-art kernel results are with this global average pooling layer for convolutional networks. And of course, it kind of makes sense. Somehow you want to take a kernel that takes into account all of the coordinate-wise pixel interactions across all pairs of images. That just seems to make sense. Here you're throwing away a lot of information. And so this is the issue with this fully connected layer. Great. So I know this was a lot of new computations, perhaps, and insight into some networks with some layer structures. But before I conclude the lecture, I just want to give some brief examples of how you can use the neural tangents library to just compute this. And in fact, what I'll show on the next slide is just an empirical discussion. Is just like everything else in this course, the theory can be a bit involved in the computation, but the practical implementation is very straightforward. And so I know I keep saying this, but at the end of the day, if I wanted to implement any of these methods, all I need to know is how to compute the kernel, because once I know the kernel, I just solve kernel regression. This involves doing 3 steps. I build the kernel training matrix. I solve this inverse problem where I want to just invert the kernel matrix and compute these coefficients alpha. And then I just build my predictor, and that's it. And now the question is, how do I actually build this kernel matrix? And this is just, we're going to see in the homework, we're going to use the neural tangents library, which we just give an architecture. Description, and then just use that to get an output from the neural tangents library, which is just the corresponding kernel function. And this will just exactly give the CNTK, the NTK, and they have a bunch of different architectures that you can try this on. You can try computing the CNTK for a ResNet if that's something of interest to you. Of course, these CNTK computations can be a bit involved, especially if you have things like global average pooling. But what we're going to do now is I just wanted to show a simple example of how powerful this method is and how easy to use it is. So let's just consider this image classification problem on CFAR10, and all of this is outlined in the lecture notes as well. But this CFAR10 data set, it's 60,000 total images, 50,000 for training, 10,000 for validation or testing. And my Ys, this is 10 different objects. So 10 class labels. And the objects in these images are like dogs, cats, birds, and so on. And these are all tiny images. So the image resolution, so the resolution is like 32 by 32 by 3. So 3 represents the number of color channels in the image. Otherwise, it's just a 32 by 32. So now what we can do is just take the neural networks that we had considered on the previous page and just sort of do this comparison. So let's first start with a fully connected network. So I have an image. I feed it into a neural network. What I do is I first consider fully connected networks. So I flatten my image. So here's X. I vectorize it. I then feed it into a super wide neural network. I'm going to take it to be 2048 hidden units here. And then it's just going to output these 10 class labels. This will be 10 class labels. So I'm going to call this architecture A. So this is a fully connected net. My B is going to be a slightly more realistic network, although it's still, I wouldn't say 100% realistic. What I'm going to do is just use a convolutional layer here, which I'm going to have these different filters. I'll call this B. And then I'm going to have a vectorization step. So I'm just flattening. I'm using that fully connected convolutional layer from the previous slide. Okay, and this is going to give me, again, my 10 classes. And what I'm going to do here is my B, I'm going to set that K to be a width of 1024. And I'm also going to do something to make my life a little easier. I'm going to do something called set a stride size of 2. And what this does is when I do convolution, it's going to shrink my image size by a factor of 2. So instead of working with 32 by 32 images here, it's going to take in 32 by 32 and shrink it to a 16 by 16 image. Okay, and you'll see that these strided convolutional operators are pretty common in image classification nowadays, and especially in ResNets, they have these as well. Now, training neural networks is actually pretty difficult. And so there's a number of standard procedures that people use. And what I wanted to do is just take all of those standard procedures and compare with how the neural tangent kernel and convolutional neural tangent kernel do when I don't do any of those standard procedures. I mean, those kernels are just equivalent. Solving kernel regression with those is equivalent to training these networks with gradient descent. Unfortunately, training some of these, especially the convolutional one with gradient descent, was taking quite some time. So I chose to go with the standard approach here. And so what did I do for the training methodology? For my neural nets, remember for kernels, this is trivial. I just solve a linear system of equations. I don't do anything fancy. But for neural nets, I have to be a little fancy. I use something called the atom optimizer. I set a learning rate of 10 to the negative 4, which is my standard trick. I use the default optimization, or default initialization for these layers from PyTorch. And then lastly, what I do is I use something called the cross entropy loss. And this is something that people do all the time in practice, and you'll see that it's like using it requires using something called a softmax activation on the last layer. And this is something that people standardly do for image classification. And for the kernel, I mean, it's a little embarrassing to even write it out, but we just solve a linear system. No tricks. You just build the kernel with the CNT or the neural tangents library, and you solve linear system. So now how do these things compare? Well, what I do also, I want to mention, is I want to give the neural network a chance to have an unfair advantage. I want to do early stopping, and I want to select the epoch where the neural network got best test accuracy. And so it might have been able to perfectly fit the training data. It's hard to say because even with this number of filters, it's a very computationally expensive process. But we're just going to give it a fighting chance to do its best here. And so now if I write out the accuracies, so let's look at the fully connected neural net. So this, when I early stopped it, I got around 85.25% training accuracy. This is all train. And my test accuracy was 54 or 0.27%. Now, if I do the NTK, of course, my training accuracy will be 100%. I'm just perfectly fitting the data. The awesome part is that the test accuracy is 59.2%. So it's around 5% higher. That's great. So it's simple to use, and you get this really awesome boost in performance. So now, if I take my convolutional neural network, I can do the same game. I early stop it. Of course, this one does much better. So this gets 88.57% and 61.6% accuracy on testing. So it's way better. So this is like so far the best one. And now I just do the CNTK. No tricks. I mean, I can probably, one can actually use early stopping in all of these techniques, but I didn't want to do that here. I just wanted to use the simple solve a system of linear equations. I'll get 100% training accuracy. And then right away, I get 65.2% test accuracy. So I get, again, I mean, this time it's a smaller increase. It's like 3.6 or 4%, but it's quite sizable. Considering I'm solving a linear system of equations to do this, nothing complicated. I mean, just look at the complications here. I have like 4 different things going on. And this is to solve it fast. Here, there's nothing going on. All of the work is done for me by this neural tangents library. And so this is one of those experiments that really demonstrates the power of this method. And I want to say that 65.2%, although it's cool for this comparison, it's really far off from what the best models, the best convolutional networks do for image classification on CIFAR-10. But the cool part is that this is a very strong kernel method on this task. And if we just wanted to establish a strong baseline, and we were trying to come up with a custom neural network architecture, that might be hard to do. There might be a lot of things. There's a lot that can go wrong here. Any one of those steps could be faulty and cause an issue. There's not that much that can go all wrong here. We're doing just a very simple thing. And so the CNTK can be used to establish a very strong baseline. And I should say the best possible, I mean, neural networks, people have studied this problem of CIFAR-10 classification for a very long time, and you can get up to 99% accuracy now. I've seen some examples of simple networks that are literally called SimpleNet. So these are deep convolutional networks that use these max pooling tricks for which there's no associated derivative, and so no neural tangent kernel. These get around 95%. And the best possible kernel now with all of these tricks is the enhanced CNTK, and this gives you around 89% accuracy, which sort of matches that. It actually outperforms, I think, AlexNet. And this is from back in 2012. But the important thing is that when you don't have this image classification problem, I actually have never really seen some concrete examples, and I'm sure many may have come out now by the time I release this video, of fully connected networks that outperform their corresponding neural tangent kernel. And especially the neural tangent kernel for this case is extremely easy to compute. Remember, it's just this recursive formula for any depth. And so we can compute the kernel on fly fast for things like EigenPro. For EigenPro, computing the kernel fast for the convolutional network is actually quite painful, which is why, especially if you use things like global average pooling, which is why you usually compute the full training kernel matrix up front and then index it and solve it with EigenPro to solve kernel regression fast. And this is exactly what we'll do in the next lecture with image completion problems. But I hope this gives a flavor of the power of the neural tangent kernel and the flexibility it offers for a variety of different tasks. And especially, I think it should be considered as a strong option for anyone who's maybe wanting to try out something simple and just get a strong baseline on some application. But this is it for lecture 6. I know there was a lot of material covered here, so I encourage everyone to look through the lecture notes. But other than that, I'll see you in the next lecture for a cool application of this method to image completion and matrix completion problems. Thank you.